Hello, everyone, and welcome to second day in Python Sweden 2020. I'm happy to introduce for you our next speaker today. It's Gunnar Grosch. He's a senior developer advocate at Amazon AWS. Welcome.
Thank you, Elvira. Great to be here.
Yeah, most welcome, and I give the word to you.
All right. So, hi everyone. My name is Gunnar Grosch, and I want you to write less Python code. That's the title of my talk. Can we get the slides up, Elvira? There we go. All right. So let's start with the abstract of the talk. So serverless allows us to build and run applications without thinking about servers. There are additional benefits with serverless that the cloud provider, AWS, can take care of tasks that we usually do with code. For instance, error handling and retries and so on. So I want to look at how serverless can reduce the Python code that we write and help us focus on the pure business logic in our applications. Short about me to start it off. As Elvira said, I am a senior developer advocate at Amazon Web Services, AWS. I have a fairly long background in the industry. Started out doing development, been in operations with cloud infrastructure and also in different management roles. I also am quite involved in the communities in the Nordics by arranging meetups and conferences and so on, primarily within serverless. I also have 3 kids at home. So to start this off, I want to look at what serverless is. Many of you probably know what serverless is, but just to make sure that we're on the same page. So a brief introduction to serverless, if you may. So these are the tenets that define what serverless as an operational model is. We talk about that there's no infrastructure to provision or manage. We don't have any servers to provision. We don't have to operate any servers. We don't have to patch them. And we also talk about that serverless has automatic scaling, and it scales by the unit of consumption. So it scales by the unit of work rather than the actual server units once again. There's no servers for us to manage. And serverless has a pay-for-value billing model. So if we value consistent throughput or execution duration, you pay for that unit. Once again, rather than paying for individual servers. And serverless as an operational model has built-in availability and fault tolerance. So we don't have to architect for high availability because the services has that built in. We still, of course, need to make sure that our total architecture is highly available. And that comes down to different patterns, practices, and so on. So when we say serverless, we talk about the removal of that undifferentiated heavy lifting that is server operations. So serverless allows you to build and run applications without thinking about servers. So looking at the compute layer or the compute services from AWS, we have this spectrum that is from the EC2 instances, the virtual machines, up to AWS Lambda. That is the function as a service compute service from AWS. And the services that are involved in serverless, the serverless compute services, is AWS Fargate, which is for serverless containers. So you run your containers, but in a serverless way. Once again, think about those tenets. We don't manage any infrastructure and we pay for value. And then we have AWS Lambda, which is our serverless functions, where we have our pure business logic and we run those functions and invoke them based on different events. And serverless is a lot more than just compute. So we have the compute layer, but we also have different data stores that are serverless. We have other integration services that we use. And when we talk about serverless, many people tend to focus on just the compute layer, but there are a lot of services that are serverless, and it is when we start tying different services together when we really can talk about a serverless application. So when we build serverless applications using AWS Lambda, we have these 3 stages. We first off talk about an event source, and the event source is what's then going to trigger our AWS Lambda function. And an event source can be different changes in data state, it can be requests to endpoints, or changes in resource state, for instance. And our AWS Lambda function, well, that's where we have our business logic, our code. And you're able to use different runtimes, but of course, Python being one of those. And then we tie our AWS Lambda functions to different services. And that can be other AWS services, and of course, different third-party services as well. And when we invoke our Lambda functions, the way we call it and then execute our code, we can do that using 3 different methods. Either the synchronous method, where we have, for instance, an API call that invokes a Lambda function. Or it can be an asynchronous invocation, meaning that AWS Lambda, the Lambda function is invoked through a service. For instance, you're uploading an image into Amazon S3, the object store, and that in turn invokes a Lambda function. Or we can have the poll-based ones, which is item processing through streams or queues. For instance, using DynamoDB, which is a NoSQL serverless service from AWS. And when items are stored or updated in that DynamoDB table, we invoke a Lambda function to process items, for instance. So an example, our simple web service, which is a synchronous invocation of AWS Lambda. A client is making a call to Amazon API Gateway, our managed API service. That in turn invokes the Lambda function and processes the code within the Lambda function. In this case, we're, for instance, storing or retrieving data in DynamoDB. A reply is sent back from DynamoDB to AWS Lambda, replies back through API Gateway and back to the client. So that's a synchronous invocation. Another one is this is an asynchronous one. Sorry, it's wrong in the title. So the client uploads an image to Amazon Simple Storage Service. That in turn just replies back to the client that we now have an object stored in S3. An AWS Lambda function is then invoked based on the object update, which in turn then perhaps stores or retrieves data in DynamoDB and then replies back to AWS Lambda. So that's an asynchronous one. All right, so that was briefly around serverless and how AWS Lambda plays a big role in the serverless applications that we build. And that brings us back to this statement. I want you to write less Python code. It's not about I wanting you to start using a different runtime. It's not about I want you to stop writing Python. It's a matter of looking at the services and the features that we have around serverless and how those can help us to minimize the amount of code that we write and allows us to once again focus on the pure business logic, the things within your application that makes your company stand out, that makes you be a great company for your customers. So I'm going to walk us through some different things that I tend to look at and tend to use when building serverless applications, things that allows me to write less code. So I'm going to start off with the example I had in the abstract, error handling and retries. So we are often used to handling errors and retries in our code. So we have these different error types. We have exceptions, we have timeouts, we have throttling errors, whatever type of errors there are. But AWS has a lot of functionality to handle these errors for us, and also to make sure that the code is retried, that the service invocation is retried. And that is something that we should use, because to be honest, the cloud provider is usually a lot better than us at handling retries, because they know exactly how the services work. So when we talk about error handling, well, there are mainly two types of errors that can occur within our AWS Lambda functions. We can either have an invocation error. That is when the invocation request is rejected even before the function receives it. Or we can have a function error, and that is when we have an error within our code or within our runtime, and that returns an error. So what I suggest that we do is that we avoid catching errors using try catch if possible. So instead of doing that, we should fail up the stack. So return the error to the invoking service and allow that invoking service to then handle the error. So let me show you an example of that. In this case, we're using Amazon Kinesis, which is a data stream service, and we're streaming data through that. It might, for instance, be image data or any type of messages that we're streaming at perhaps a high throughput into our application. Based on that, we have this poll invocation with AWS Lambda. So our Lambda function is then invoked for these messages that queue up through Amazon Kinesis. Well, in this case, my Lambda function contains code that is supposed to store these messages in S3, the object storage. But for some reason, there is an error. I might not be able to process the message, it is malformed or something like that. Well, instead of handling that error within my Python code, catching the error and so on, I should then fail up the stack. So I simply let the entire function fail and then return that message back to the invoking service, in this case Amazon Kinesis. And then Kinesis, as the invoking service, well, it has this built-in retry functionality to reprocess events. So instead of catching errors, we can then fail the entire function and fail up the stack. To do this, of course, it means that our Lambda functions can't contain too much code. We can't put in too much functionality within each Lambda function. So we often talk about having lean functions, creating Lambda functions that contain one single purpose, and instead having multiple Lambda functions, and they all contain that one single purpose. This isn't always possible. Sometimes we need to do multiple things within one Lambda function. But if possible, always aim for building these lean functions so that we're able to fail the entire function instead of catching errors and handling them ourselves. And that then brings us to retries, automatic retries. So the retry behavior, it differs depending on what type of invocation we're doing with AWS Lambda. So I mentioned the three invocation methods before: synchronous, asynchronous, and poll-based ones. So the synchronous invocation, the example I showed was API gateway invoking a Lambda function. Well, that returns the failure to the invoker for retry. So think about a web page calling an API. Well, if there is an error, that error is sent back to that web page, to the front end of your application for handling the error. For instance, instead of the API returning a 200 response, it's returning a 404, a 502, or something like that. And that then needs to be handled on the client side or on the front end side of the application. With our asynchronous invocation, Lambda will retry the function error twice. So it will try to process the event once again. The example I showed before was an object being uploaded to S3, which invokes the Lambda function. Well, if there is an error within that Lambda function, it will try to process that event once again for up to 2 times. And usually this is straight away after the first error, but it might sometimes, depending on the queues and how many events there are, it might take some time before the sequential retries happen. And then we have the kind of events where we read from a stream. I mentioned Kinesis before and DynamoDB, which are services that can invoke Lambda through streams. And in those cases, Lambda will retry the entire batch of items because we aren't sending these events or messages one at a time. Instead, Lambda will get them in batches, and then we're able to retry the entire batch. And to help with this, there are some additional configuration we can do. We can, for instance, configure the batch to bisect on function error, meaning that it will split the batch where the error is. So we're able to then reprocess the events separately. We can also set a maximum record age. How long will it continue to retry these records? And we can set a maximum retry attempts. How many times should it retry? And this will be, for the record age, it can be anything up to 7 days. And for the retry attempts, it can be up to 10,000 times. So using read from streams means that we can be quite sure that the event will be retried over and over again, depending on the configuration we have. If we're still having errors, well, then we're able to set a destination on failure. So we can store the event or the event batch on a separate location to then either process it again or to inspect the events. And for the event sources that read from queues, we have the different managed queue services from AWS, for instance, Simple Queue Service or Amazon MQ. Lambda will retry the entire batch of item there as well. And it will do that send it back to the queue and then retry it up to 1,000 times. So thinking about this, then adding the different SDKs to this, which have different retry behavior depending on the runtime and the services we use, means that it's important how our Lambda function code works. Since we have this retry behavior, it's important that we build for retries. So our code should be able to retry and reprocess events without affecting the outcome. We want to have these idempotent commands or processes, meaning that we're able to do the same command multiple times and have the same outcome. Think, for instance, about activating an account. So even if we do that multiple times through retries, it should always just activate the account. It shouldn't switch it back and forth, for instance. And that becomes a bit harder when we, for instance, talk about adding money into a bank account. Well, the way we form our code then, it needs to still work with that retry behavior in mind. We shouldn't add $10 each time it retries. It should just add $10 once. And this brings us to the second topic, another feature of several of the services that helps us reduce the amount of code we write, because the services in themselves take care of the load of several of these features. So this is dead letter queues, and that's a common capability within queuing and messaging services, and it allows us to handle failures in event and message receiving services. So it provides a way for us that failed events or messages can then be captured and sent to another system. And there we can store them for future processing. So with dead letter queues or DLQs in place, we can have greater resilience and reliability and improved recovery from any type of failure within our system. So several of the services have support for a dead letter queue, something that we can just simply enable on the service. So for instance, we can add dead letter queues to SQS, the simple queue service where we're able to queue events or messages, simple notification service, a messaging service where we're able to send messages throughout our application, and AWS Lambda, which we've talked about several times. We're able to enable dead letter queues there as well, and a service called EventBridge, one that I'll show you a bit about in shortly. So these are 4 services that have support for dead letter queues, something that we easily can create just by configuring them. So when messages fail to process or fail to be delivered, they can then be sent to dead letter queue. So this means that we don't have to write any specific code for doing that. Instead, we just enable it on the service. And well, the different services, they use, most of them use SQS as a dead letter queue. So the events that we need to send to DLQ, they are stored in another queue instead. Lambda also has the possibility to use SNS, so to send a message as a dead letter queue instead as well. So an example of this, in this case, we have an asynchronous invocation through an object in S3, which invokes AWS Lambda. Then Lambda is supposed to use SNS to send a message somewhere. In this case, send a text message or an email to a client. And in this case, the client is unable to receive the message. So we have an error, a failure of delivering this message. Well, we can then simply configure SNS to use a dead letter queue, so that this message, instead of just disappearing, or that we need to handle what should happen to that message within our code, it will then just be sent to a queue within SQS, and we can then inspect the message, or we can reprocess the message. If there's a failure, for instance, that resolves itself over time, well, then we can reprocess the messages. So that's an example of how we can use dead letter queues. And once again, less code for us to write. And then we have something called execution record routing. When we execute code, we always have some sort of output of that. And we also have the input, that is the event that is sent to the code to be executed. Using AWS Lambda, for instance, we have the event that is sent that executes our Lambda function, and then we have the output of the operation that we're doing. So we have a feature for AWS Lambda that's called AWS Lambda Event Destinations. So this is something that we can use to then take the output of each Lambda invocation and then use that. This is for our asynchronous Lambda invocations, so the ones we saw, for instance, where an object was uploaded to S3. And the record that I'm talking about, it contains both the request and the response, and this is in JSON. And we can then route this record to different targets based on the function result, for instance, on success or on failure. And we can use different targets. We can, for instance, use another Lambda function, we can use a queue or a notification, or we can use EventBridge. And this is something that we should favor over using dead letter queues that I talked about just now, because this gives us even more control over the event and the record that we use out of Lambda. So an example of that, in this case, we have a simple application where users upload images to S3. Then our Lambda function processes the image. Let's say that we want to create thumbnails. So we have this short, simple code within our Lambda function to pick up the image, process it, and store it then in another bucket. So an image is uploaded, that invokes AWS Lambda, and we're supposed to store that in another bucket. And in this case, it worked. We're able to store it there. So on success, we can then route that record, in this case, to another Lambda function. Let's say that Lambda function will then pick up the thumbnail that was created and do something with that. So based on the execution result, in this case on success, we can route that record there. But if it fails, well, we can set up an on failure destination. So in this case, let's do an example where we then send that record to a queue, and then we're able to use that in with the same way as I showed with the dead letter queue example, where we're able to inspect or reprocess the events. So using Lambda destinations, it means that we can then use the output of our Lambda function execution and use that for different use cases. And this is also a great step towards building applications that are more event driven. So both of these are events on success and on failure, and we can use those events to then start building perhaps more complex or at least more advanced applications as well, but still with less code. Another example is data consistency. When we build applications that are event-driven or command-driven, we often want to decouple our applications so that the applications are smaller parts that work independently from each other. So we do this using different methods and techniques. Using AWS Serverless services, for instance, we often use simple notification service, SNS, and SQS queues, and so on to do that. But in many of the architectures and applications we build, data consistency is a common business requirement. And this can be translated often into a technical requirement, such as 0 messages should be lost. We should have strict message ordering, for instance, that in the order that messages are received into a queue, that's the order that it should be processed as well. So to help with this, we have the option of using either standard or FIFO queues and topics, that is for SQS and SNS. So we can have the option of using FIFO, and FIFO stands for first in, first out, which gives us this strict ordering, and it also gives us the opportunity to have only once message processing. Because a standard queue, well, it means that in the same way as I talked about before with retries, it means that a message will be delivered at least once. So we know that the message will be received at least once, but it can be received twice. So once again, those idempotent functions are important, where we should be able to process a message more than once. But with certain applications, that's hard. We need to have this only once message processing, and that's where FIFO queues is able to help us. And we can then add FIFO to either our SQS queues, and there are certain differences between the standard queues and the FIFO queues, for instance, in the message throughput. So we should choose the correct one. But having the option of using FIFO means that we don't need to handle that in our code. We don't have to make sure that things are processed in the correct order. And with SNS, well, it's the same, that we have on the topic level, and the topic that we've created for our messaging, we can then use either standard or FIFO, and there is a difference in the throughput there as well, using that publish API that SNS has. But once again, we don't have to write code to make sure that the ordering is strict and that we have only once delivery. So I mentioned decoupling before, and decoupling is definitely a part that is becoming more and more important the larger our applications become, because having a tightly coupled system means that, well, it's of greater risk of failure in that each part of the system relies on the other parts. But having a loosely coupled system, it's one where each component has little or no knowledge of the definitions of the other components. It only knows how to communicate between components. And to decouple, we have several different services. I've mentioned all of these except the last one. We have SQS, we have SNS, we have EventBridge, and then we have a service called Step Functions, which I'll show you a bit about in a short while. But these services help us then decouple our applications through queuing, through messaging, and so on. So when we talk about decoupling, we talk about it usually either through contract decoupling, where we set up APIs between different services, or we talk about runtime decoupling. And runtime decoupling is usually the asynchronous invocations, while contract decoupling is most often synchronous invocations, where the two parties need to be there to be able to respond to each other. But with the asynchronous invocations, well, then if we're storing messages in queues, for instance, it means that service A and service B doesn't have to be there at the same time. So that gives us better reliability. And to decouple, well, we have several ways of using those services that I just showed. That means that we can do it in an easy fashion. For instance, using Lambda destinations that I talked about a few minutes ago, we can easily then decouple applications by using queues, for instance. So here's an example of how we can decouple an application, where we then have an upstream service that is doing something. Let's call that service A. And that service needs to communicate with service B, which is the downstream part of this, our Lambda function and our DynamoDB table. Well, by simply putting a queue in place in between, we're decoupling those services, because the Lambda function, it will pick up those messages from the queue and then process them. And the integration between, in this case, the queue service and AWS Lambda, well, that is something that is built into the service. So we don't have to build the way that we pick up those messages and how we use those messages until we need to then, of course, read the message within our function code. But that is something that is in place with the service. Once again, less code for us to write. Using that architecture, we can replace the queue with some other services, in this case Amazon EventBridge, which is a service where we're able to fan out using the messages that we send through that service. So we can use the same message and have that then invoke several other services, for instance Lambda, Step Functions, and we can even send the message to a different queue, a different part of our application. And all of these are service integrations that are in place with the services that makes it easy to create the integrations in between. So that brings us to the event bus. And if you ever worked with event-driven architecture or try to build your own event bus, you probably agree with me that it can be quite difficult to manage events and at least manage events at scale through code. So having an event bus in place as a managed service means that it's a lot easier to manage those events. And the EventBridge, the service that AWS offers is Amazon EventBridge, and that is our event bus and router that allows us to then route events through the service from several different other AWS services. We can have custom events that we push into the service, and we have built-in functionality for different SaaS applications as well. So if you're, for instance, using a specific ticketing tool, monitoring tool, and so on, observability, well, those events can then be pushed into this system and used within your event bus. Let's say, for instance, that you receive an alert within your observability tool or monitoring tool. Well, that can then be pushed as an event into the event bus, event router, EventBridge, and that can then trigger an AWS Lambda function, for instance. So within the EventBridge service, we then set up different rules for how to handle the events that are within our application, and we can then push them to different targets. And the targets, they are a whole bunch of different AWS services within the serverless spectrum, but also services that aren't serverless. And we can use other services as well and use them with these events. And a great thing about EventBridge is that you can set up your custom events. So you can even add events that come from any type of service. It can be any type of application you already have, legacy applications, it can be on-premise applications, and so on. So using EventBridge makes it a whole lot easier to manage events within your application. There's also a feature for managing the event schemas, because if you worked with events in any type of application, knowing how to handle events, how they look, what they contain, and so on, that's also a struggle and something that we often need to then handle with the help of our code. With the help of schema registry and discovery, means that we're able to easily create this centralized schema registry where we can store how each event is supposed to look, which helps us integrate different parts of our application, different services together. It also has a built-in function for discovery. So even if an event is completely new, we're able to discover how that event looks and then store the schema out of that event. It has built-in integration for several IDEs, so it's easy to use this as well while you're developing your application. And next part in regards to events then, well, it is how do we store events in case of failure? Well, because if things happen, in event-driven architectures, usually an event is something that others observe and then that disappears. But in some cases, we might have different type of failures. We might need to reprocess events or replay them. And EventBridge has support for that as well through archive and replay of events. So we can create a simple archive where we're storing our events. So we don't have to build that functionality using any other type of service. We don't have to write and own code for archiving and storing our events. And the events that we store, we can either store them indefinitely, or we can set up a retention period. And we can set up filters and so on for which events to store. The events that we then store in our archive, we can easily then replay them as well. So for instance, if we have failure, well, we can reprocess the events to then make sure that every user is updated or every account is processed and so on, even though we had a failure earlier on. And this is something that we can use with any type of events that we use with EventBridge. So the custom ones, the ones through other AWS services, or from SaaS integrations. And this then, now we've talked about a lot of different services, a lot of different parts, and the architectures that we build, they can become quite complex. So it brings us to the last part, which is orchestration. So orchestrating a series of individual applications, services, or functions, and so on, it can be quite challenging as the application grows. So as the distributed application becomes more complex, the complexity of managing them also grows as well. So that's when we often look at state machines. And state machines, that is simply a collection of different steps that we split into discrete states. So we have a starting state and one state that is active all the time, and then we end the state machine in the end, of course. So think about it as a workflow or a flow chart, for instance. So AWS offers a service called AWS Step Functions, which helps us do this type of orchestration. Because, as I said, managing these architectures that can become quite complex with different parts, different functions and services, managing them through just code and through the way that you build your architecture can be challenging. But using state machines makes it easier to then orchestrate them. So Step Functions is a fully managed service where you can create these state machines with the different steps. It has built-in error handling and so on. And you have integration to many of the different AWS services, which makes it easy as well. And you can integrate this with your IDE to even get a graphical overview of the state machine that you're building using AWS Step Functions. So doing this instead of writing code for handling how these workflows, these state machines should work, makes it a whole lot easier to then build a more complex orchestration of your entire application. So, a lot of information in quite short time, so just a brief summary. Serverless removes that undifferentiated heavy lifting that is server operations. You don't have to manage any servers with serverless. Make use of the built-in error handling and retry behavior. Use dead letter queues, simply connect that to the service that you're using so you can capture events and messages. Use AWS Lambda destination so you can route and then do next step based on failure or success. Use FIFO queues for data consistency and FIFO topics. You should try to decouple your services with the different services that we have for events and messages. And you can use EventBridge as a way to simplify the usage of events within your event-driven architectures. And you can orchestrate your services using step functions. All of these are services and features that allows you to write less Python code, which was the whole meaning of this talk. So, my name is Gunnar Grosch. I am a senior developer advocate at AWS. And thank you for attending this talk. And let's see if there are any questions.
Thank you very much for today. It was very interesting. If someone will have questions, people also can ask you in Slack, and we're waiting on questions.
Right. Thank you very much.